This is Timothy Wood with the Citadel Civil Engineering Program. This is CIVL202 Statics, and in this lecture we're going to discuss the equations of equilibrium for a non-concurrent force system. A non-concurrent force system. So we'll remember that for a non-concurrent force system, we're modeling with rigid bodies, and we're going to have two different equations. First, we're going to say that the body will not translate. Therefore, the sum of the forces is equal to 0. Yay, nothing moves. Additionally, the body will not rotate. So the sum of the moments about any given point is equal to 0. Yay, nothing moves. And these are our basic equations. Now, the thing for us to keep in mind is that these are vector quantities. So we'll want to be able to talk about this in terms of our various directional components. And in 2D, that means basically three directions. Now, you're going to ask the question, 2D, three directions. I'm so confused. Let's walk our way through it. So the first thing to acknowledge is that in 2D, our coordinate system looks like this, X, Y, and Z. And so when we're resisting translation, our sum of the forces is going to have two components, right? The sum of the forces is equal to 0. So we're going to say that the sum of the forces in the X direction is equal to 0, and the sum of the forces in the Y direction is equal to 0, or 0I plus 0J. This is our Cartesian vector notation, CVN, form of the equation, Cartesian vector notation. And we'll have to remember, though, that these are actually two equations. It looks like one line, but it's two equations because these two terms are orthogonal from one another. Therefore, we could also express this in scalar notation. We would say the sum of the forces in the X direction with an arrow is equal to 0, and the sum of the forces in the Y direction, again indicated with an arrow, is 0, and we get two equations. So this captures the idea that there's no translation. Now, let's think about the sum of the moments. We know that our sum of the moments is equal to 0, but let's remind ourselves, in 2D, do we have any rotation about the x-axis? That's a 3D behavior. Do we have any rotation about the y-axis? Well, that's a 3D behavior as well. But what we do have is rotation about the z-axis. So it turns out that in Cartesian vector notation, we're going to have the sum of the moments about the z-axis times the k unit vector, because our moments are indicated by the axis they're rotating around, using our right-hand rule. So sum of the moments. So that's one equation here. In scalar notation, we'd write it something like this. Sum of the moments, and then we draw our positive sign convention curly Q for 2D, counterclockwise positive. So our sum of the moments is equal to, yay, 0, nothing rotates. So nothing's translating, nothing's rotating, and we notice here that we now have three equations of equilibrium. So when we were doing 2D particle equilibrium, we had two equations. When we were doing 3D particle equilibrium, we had three equations. Now we're doing 2D, again, this is 2D rigid body equations of equilibrium, EoE. And in this case, we have three equations, sum of the forces in the X, sum of the forces in the Y, and sum of the moments. Now, I will note in your textbook, it talks about the fact that you can actually write three independent sum of the moment equations, but the bottom line is you're never going to be able to write more than three independent equations for a 2D rigid body equations of equilibrium using statics, which means that we can solve for up to three unknowns. So because we have three equations of equilibrium, that has to be greater than or equal to the number of unknowns we're attempting to solve for. And again, those number of unknowns is expressed in our free body diagram typically as the reactions. And so one of the exciting things that happens out of this is that there are two systems that we commonly analyze using statics. One is simply supported. It would be a beam that looks like this. This is a simply supported beam with a pin and a roller. We'd acknowledge that our free body diagram, it resists translation, so two forces there, and the roller only resists translation up and down. So that's a total of three unknowns, so we can solve for that one. The other system we might solve for is a cantilever, like so, in which our three unknowns are going to be the horizontal reaction force, the vertical reaction force, and then also the reaction moment that resists rotation on this little cantilever. But again, that's 3 unknowns. That's something we can solve for. All right, I look forward to working these problems with you, where we draw our free body diagram and then we use our free body diagram to write our equations of equilibrium. We use our mathematical prowess in solving systems of equations to solve for unknowns. And then we've just shown that we actually know what we're doing when it comes to applying statics. And so if you can master these concepts, if you can get in the practice and show off on the exams, you can start telling people, I know how to do statics. That's what we're talking about. All right, I'll see you in class. Take care.